and welcome to our Chapter 8, our first lesson in Chapter 8. The next two chapters in our book are really about the work of a statistician, that is inference, drawing conclusions from samples using mathematically sound methods and saying that sample data either backs up what is believed to be true or maybe gives us a value for a proportion or a mean in the next chapter for the population, which couldn't maybe otherwise be measured. So our work here in chapters 8 and 9 very important. We're going to start today by talking about how you can estimate the population proportion, and it says with confidence, right? We want to be confident of our estimate. We're going to begin here. Suppose we're flipping a fair coin 40 times. I'd like you to think about what's considered reasonably likely or plausible for the sample proportion of heads flipped. There should be an S there. I just want to draw your attention or have you think back to that normal curve that we know quite a bit about already. We've said before that things that are likely, quote-unquote likely, happen between 1 and 2 standard deviations of the mean in the standard normal curve, and that the z-scores where those things happen are at positive and negative 1.96, right? That gives us 95% of data between those two z-scores, and that's what's considered to be reasonably likely. So if we're going to answer this question, we obviously have to think a little bit about a z-score. So I want to just write out the formula for z and have you remember it. A z-score is a data value, in this case that will be a p-hat coming from a sample, minus the known proportion, okay, what we know to be true, and in coin flipping, of course, that's going to be 50%, over the number of standard deviations from the mean. If we're talking about a p-hat distribution, that's the number or the amount of a standard error. Now, what we're asking for are the likely proportions, so we want to really come up with p-hat here and see which p-hats are likely. So I'm going to run this twice, but I want to solve my formula for p-hat knowing that I've got a positive and negative 1.96 to work with, so hence I said we're going to run it twice. We know that that will equal what we're interested in, a sample proportion, minus the known probability or proportion of heads we should get, a 0.5 over a standard error. And if you recall from the last chapter, standard error for a proportion is p times q. That would be 0.5 times 0.5 divided by sample size, and we're flipping 40 times for p-hat. So I want to just go ahead and write out a formula for p-hat here. We would take the denominator here, multiply it by 1.96, and it's plus or minus, it says, so we'll worry with that worry about that in just a moment. Plus or minus 1.96 times, and it is 0.5 times 0.5 all over 40. Now we've taken care of the multiply. The only thing left to do is the addition of 0.5, and we'll put that up here, adding 0.5 to both sides. We have a little formula that will get us plausible values for the sample proportion of the number of the proportion of heads flipped when you flip a fair coin. I'm going to go do that in my calculator. I'll catch up with you in a minute. Okay, I'm back. As you can see from my calculator screen, just doing the little arithmetic there, we can see that our p-hat reasonable proportions would be in the interval from 0.35 about, or 35% of the time, and I'm going to write this in interval notation, or I'm going to write this in an extended inequality form. Likely proportions go from about 35% to 65% heads. If we're flipping a fair coin and we flip 40 times, then we can be pretty sure, 95% sure, that the proportion of heads would be, or likely values for the proportion of heads would be between 35 and 65%. Now as far as numbers of heads, well, to do that we can just take what we have, 0.35, and multiply it by the number of times we're tossing, and do the same thing with 0.65 times the number of times we're tossing, and I'm back, and you can see that if things are working the way they should based on the laws of mathematics, the number of heads should be between 14 and 26 if things are operating fairly and we flip 40 times. We want to talk about a couple of different ways here of saying the same thing, but maybe in the way that a newspaper or a news article would report a survey. That is, we know that 50% plus or minus 15%, if you think about that, that's true. 50% is the center of this interval, and this is 15% lower, that's 15% higher. 50% plus or minus 15% of 40 flips should be heads. Another way of reporting that same piece of information, 50% of flips should be heads, with a 15% margin of error. You maybe have heard that, 15% margin of error. That just means that we're thinking about some interval that halfway, because heads and tails have a 50-50 likelihood, so 50% should be heads, but we would be comfortable with results between 15% lower than that, 15% higher than that. So kind of what we're doing here is coming up with an interval that we think will contain likely results. Okay, and what I'd like to show you next is a table. This table's been developed based on sample sizes of 40 to show the proportion of successes in the population. So if this is what you believe is true in the population, and remember a moment ago we were here at 50% with our heads, this table will show us the number of successes that are reasonably likely, or the proportion of those successes that are reasonably likely. And you can see that we have it marked off here. 40 flips with a 50% margin, or a 50% likelihood of occurrence. It came up with, guess what? That'd be 8, that'd be 12, so 10, 12, 14. That sounds familiar. To 26, and I believe that's exactly what we said just a moment ago. 14 to 26 successes would be considered reasonable. If you look down on the proportion side, they're showing between 35 and 65%, and I believe, if I'm thinking correctly, we said also 35 to 65%. Imagine that. And so folks, someone has gone through and come up with likely values for all the possible, well, not all the possible, but 5%, going by 5% in population proportion, and they showed us all the range of likely values. That's what this table is for. So it shows the number of likely successes or, actually it's and, or the proportion of likely successes for some binomial experiment that's performed 40 times for sample sizes n equals 40 at various levels of p. Okay, now we're going to use this table, so I'm going to come back to it a couple of times. I want to have you take a look at some examples, and here comes our first one. According to the 2000 census, about 60% of Hispanics in the U.S. come from Mexico or have Mexican origin. Would it be reasonably likely that in a survey of 40 randomly chosen, that's good, our table can help us with samples of 40 randomly chosen Hispanics, is 27 a likely number? Now I want you to note the features here. Our proportion of success in the society is 60%. We want to know if 27 is likely. So I come back to my table. I'm going to look along the 60% population proportion, and I'm wondering if 27 is a likelihood. Well, that's 28 right there. 27. Sure enough, it crosses that likely range. So based on our table, we can say, yes, 27 is likely. Okay. Another example, according to the same census, about 30% of people over age 85 are men. That means the other 70% are women. In a random sample of 40 people over age 85, would you be reasonably likely to get 60% who are men? We're not talking about numbers now, we're talking about probabilities or proportions. And as we come back to our table, our population proportion was 30%, so we're on this line. And what we're wondering is if it's likely to get a 60% of a sample of 40 falling into, nah, that's not happening. The 60% line out here, that's not in this bar, which shows reasonably likely occurrences. So 60% of men, that's not like, you would not be reasonably likely to get out of a group of 40 folks over 85, 60% of them are probably not going to be men. Okay, it would be unlikely. Here's our last one, last chance to practice this here. Suppose that in a random sample of 40 toddlers, 34 know what color Elmo is. I do. We want the 95% confidence interval. Well, that's different language, but it's the same thing that we've been talking about. The 95% confidence interval for the percentage of toddlers who know what color Elmo is. This time we have 34 of 40 that we know from a sample. Now that's a slightly different use of this table. 34 of 40 kids in a sample knew that, and so I'm going to just draw that vertical line right there. And folks, what we can say is when our vertical line touches one of these red bars, then that percentage is within the 95% confidence interval, or the 95% confidence interval based on the sample is between, well, let's see, we touched there first, and that's 75%, and we touch here, which is 95%. So what we can say, see, we were reading over on the left scale there, that means we're coming up with a possible range of population proportions between 75 and 95% of toddlers of all toddlers. See, we're trying to predict for everyone here. 75% and 95% of all toddlers know what color Elmo is. At least based on this sample. And I'd say that sounds pretty accurate. So as you look at the three uses of this table, we used it three different ways, really. Here we were looking for likely values. Here we looked for likely proportions. And finally, here we looked to predict a population parameter. That is, we predicted that in the population of all kids, 75 to 95% of them should know Elmo's color. So we predicted a population parameter. And that's big stuff, folks. We're heading where we want to go. Suppose a poll of 40 randomly selected statistics majors finds that 20 of them are female. The poll reports that 50% of the statistics majors are female, which is accurate according to what they have. 20 of 40 is 50%, with a margin of error of 15%. It asks us to use the chart to explain where that figure 15% came from. So I'm going to get back to my chart real quickly. So the report said that 20 of the 40 women, or 20 of the 40 students, were women, and they reported that as 50% plus or minus 15. Ladies and gentlemen, here's the 50% mark. And we have 1, 2, 3 bars above and 1, 2, 3 bars below, each of those bars, of course, being 5%. That's where the margin of error came in. Here's the central figure. Here's the margin of error. 50% was the center of the interval. With 15% above and 15% below. Why do we say we want a confidence interval for P, the population proportion, rather than saying we want a confidence interval for P hat? Well, P hat, folks, comes from a sample. If we've got a sample, then we know what P hat is. What we're trying to do, we want to predict the population parameter. So we predict P based on P hat. That is, we predict about the population proportion based on a sample's proportion, and that's really the heart of inference. Okay? Predicting for the population based on what you get from a sample. That ends our lesson for today. I would ask you to get out there and do the U-Try as quickly as you can, and we'll see you in school tomorrow.